Okay, good morning. Welcome everyone to the next lecture on Introduction to Artificial Intelligence. Today we will start, or today we will discuss one of the more complicated aspects of the models that we have introduced so far, and today we will deep dive into POMDPs. I want to apologize. I have a cold, so I will from time to time need to make a break to blow my nose, so sorry about that. Anyway, let's dig in. So what we have already covered today, so far, sorry. So we have focused on single agent decision making, then briefly we talked about games, and we covered deterministic cases, stochastic cases. We learned about reinforcement learning. We learned how to sample the state space and how to deal and solve very, very large single agent problems, and also games. And throughout the last lecture, you have learned how to deal with uncertainty, how to deal with probability, how to reason about probability. And today we will basically combine all of this to solve POMDPs. And this is basically the main point of this lecture. The main point of this lecture is to show you that you can combine multiple aspects to solve much larger problem, right? So this is why we are talking about POMDPs. Of course, MDP was the main formal model for us, but in a real world, you very rarely are able to perfectly observe the state of the world. It's more common that you don't know some aspect of the environment of the world, and that's why POMDPs, or partially observable Markov decision processes, are more practical, more applicable, and more realistic. Of course, also more challenging. So we already had the definition of a POMDP in our second lecture, but to remind you that we can define POMDP using a set of states. Again, we have set of rewards, actions. Similarly to MDPs, we have discrete dynamic in the problem. So whenever agent makes a action, the state can change, the inner state of the problem can change, and the agent receives some reward. What is different is that, in POMDPs, the agent cannot perfectly observe the state of the world, and the agent has only a belief, which is a probability distribution over states, right? So the agent only has some subjective perspective of what are the possible states and what is the probability with which the agent can be in some of these states. And the agent updates and changes and refines its beliefs based on observations, right? So we have some finite set of possible observations that the agent can receive, and based on the action and our prior belief, we can get some observation and then update the belief of the agent. And previously, we have discussed that we are able to exactly compute the new beliefs. So if we are in some state or in some prior first belief B, then we can compute the new belief after performing action A and receiving observation O, and this is the formula how we can compute it. And this is exactly why we are waiting until you have covered Bayesian rule and Bayesian networks and reasoning with probabilities, because this follows up from the Bayesian rule. Okay, so this is the basics, the theory that we have already discussed, and let's continue and let's dig deeper how these beliefs actually can be computed and how we can use them to solve POMDPs. So we will use our well-known example from the maze with the robot. So we have a robot that doesn't know like where in the maze it is, and this robot can only perceive its surroundings. So we have state as we had before. We have coordinates x, y, direction, and the fact whether the robot has already collected the gold or not. And we can have 4 actions, either turning the robot or move forward and backward. And the robot can like receive and observe its surroundings, its 4 neighborhoods. So in front of the robot, on the right side, behind it, and on the left side. Right. So like these are 4 tuples of the possible observations. So it can either see wall or empty space in either of the 4 directions. Okay, so this is our example that we will be using, and let's assume for now that let's say that we have this is our current belief, right? Like we'll now like exactly specify how the beliefs are updated and what is the exact formula. So we will not just like hide that this is a normalization constant and so on. Like we will write it down fully, and let's assume that this is our belief, which basically means, like that the robot can be one of these 4 squares, and like for simplicity, I'm disregarding the direction. Like to be perfectly, precise, I would have to say that like with which direction the robot is in, for example, this square with probability 25%, right? But for simplicity, let's assume that disregarding the direction, like the robot can be in one of those 4 squares. And let's say that the robot performs the action move forward and receives observation like this, which basically means that after performing that action, the robot sees wall in front of it and on the left side, right? So if the robot sees these 2 walls and nothing behind it and nothing on the right side, then like the new belief would look like this. So the robot can be only here or only here, right? Like it cannot be here, it cannot be here, it cannot be here, and so on and so on, right? So this is the change in the belief that the robot will compute. And how can we compute it? Well, we'll just like use that formula, or basically condition like the probabilities with which the robot can be on those new states. So if I take the probability for this particular state for 1, 1 and direction that way, then like we know what kind of observation we received. We know what are the probabilities with which the robot can get to a particular state from some other state. So like from state 2, 1, which is this one, and facing, or the direction is on the left, then like this is the probability that the agent will actually move from this state to our like state for which we are computing the belief. And we need to take into account like what was the original belief with which the agent thought that it actually is in this state, right? So this is the 3rd part, and you can see that like if we multiply everything together, we will get like 0.25, and this 0.25 is basically the same number as for this one, right? And this is not really a probability distribution. So that's why like we need to normalize these new beliefs, and after normalization we'll get like 50% here and 50% here. Okay, so this is like to illustrate and to demonstrate that we can like use beliefs, and we can reason and update these beliefs, and these beliefs basically change how the agent receives new observation, and depending on what actions the agent performs. And like with this, we can like move on and to discuss how can we like use these beliefs to solve POM-DPs. Before we go there, any questions to this? So, is the belief update clear? We take our original belief, we take into consideration what are the probabilities with which we move from one state to another state after performing some action, and then basically normalize to get a new probability distribution. Okay? Okay. So, for like when we want to solve POM-DPs, it's good to get the inspiration from MDPs. And when we were solving MDPs, we were looking for value function. We were looking for the best action to be played for each state, right? So the value function basically, like if we have perfect value function, some evaluation what reward the agent can get from each particular state, then like the optimal state value function was like that value function that was maximizing this reward for the states and for the agent, and following that optimal policy in a greedy manner, or that optimal value function in a greedy manner, basically gave us optimal policy. So this is like the solution. This is what we were looking for with value iteration or policy iteration for MDPs, or with learning, like when we were trying to approximate like which action is the best one to be played in every particular state, right? So this is what we want, right? This is what we want to find, either a value function or the prescription for actions to be played in every possible state. Okay, so this is like the baseline. So how things change for the POM-DPs. So what's different? So the main difference is that we don't have the states. Instead of states, we have beliefs, right? And let's consider like this situation. I slightly modified the example, so I removed one wall here, and let's assume that we have this this belief, right? So the agent can either be in this square facing left or in this square facing right. And let's consider like two possible actions. Let's consider that we want to decide what's good, what is the best action to be played, and let's assume for simplicity that we are considering only like move backward action or turn right action, right? We can consider all the others, but like for now, let's assume just these two. So, like, how do we decide like which one is the best one? Because in this state, so like we know that with 50% probability we are in this state, with 50% we are in this state, and for this state, or this 1-1 state down there, it's actually better to turn right, because then like we can move forward and get to the goal, or collect the gold, right? For this state, the better action is to move backward, because we will get to the goal directly, right? So really, like which action is better depends on the state. And we don't know in which state we are, but we know what is the probability with which we are in some particular state. So instead of computing like rewards for actions in each state, we can compute expected reward for each action. Because we have expectation, we have some probability that, okay, like with probability 50%, I'm in this state, and in this state, the reward would be 10. And with 50% probability, I'm in a different state, and in that different state, the reward would be 0. So my expected reward is 5. Right? And this is how we can work with that, right? Because we know what are all the possible states, and we know what are the probabilities with which we are in those states. Like, remember that like we are dealing with models where we assume that we know all the possibilities and we know the probabilities, so we can compute these expected rewards. Okay, so we can basically use and compute expected rewards for every action in every possible belief. It's just expected reward instead of actual reward, as was true for the MDPs. So this is good, right? Like this is good. We can basically say that, okay, like for each action and for each belief point, we can compute expected reward for that action and then select the best action for every belief point. And this is good. This is very similar to what we've done for MDPs. For MDPs, we can also like evaluate what is the reward for every action and select the best one, right? So the same thing we can do also for POMDPs, right? So okay, instead of looking for value function that was a mapping from states to rewards, for POMDPs we have mapping from beliefs to rewards, right? So from some probability distribution, for example 50-50 or 49-51, we will have, for some policy, we can have expected reward and we can have a value. So we can basically write down the Bellman equation also for POMDPs in the very similar way as we did for MDPs. And the only problem, quote unquote, is that we are in the continuous space. Because like we cannot enumerate all the possible belief points because it's continuous. So we can write it down, and formally this is true, this is valid. We can compute it mathematically. But it's not very practical. But it's good that, you know, like mathematically and theoretically it works. Because like we will move from there and we will use it. Because if it wouldn't work, then like we cannot even like follow up and use all the other tricks that we will discuss later. So it's good that it works, and it's basically like a very similar thing as for MDPs. Okay? So again, like this equation for POMDPs is basically the same thing as for MDPs here, right? Like you should be already familiar with this one, where we are, you know, looking for optimal policy, maximizing or finding the best action, and iterating through all the possible states that we can reach, and evaluating the rewards that we can get for reaching these states, right? And for POMDPs, the main difference is that we are like integrating through possible belief points, because like this is the continuous variable, and we don't have enumeration through like specific probability distribution, specific belief points. Okay, so what we have done so far is that we have reformulated the POMDP as a MDP with a continuous set of states. So POMDP is really like the same thing as MDP. Is just, you know, like for MDPs, if you recall, our definition started with that we have finite set of states. So if we expand that and we said, okay, like we can have infinite number of states because the states is some continuous variable, then this is what we have done. Right? So it's very, very similar. Of course, as I talked before, like we cannot really like easily solve problems with continuous variables. We cannot really integrate properly and on the scale. So we need somehow to deal with this continuous variable. And with you know, computer scientists and discrete mathematicians, like the first obvious choice how to deal with a continuous variable is to discretize it. Right, like this is the obvious choice. Like very often you, when you need to solve some problems with continuous variables, you will just like discretize it, take, for example, values only like with the step, let's say 0.01, and you have then finite problem. And we know how to solve finite problem, but it would be huge, right? And in here it would be really, really huge because the beliefs are our half dimension of with respect to number of states, right? Because like belief is a probability distribution over all possible states. And if we have, let's say, a reasonably large POMDP problem with tens of thousands of states, then you technically want to discretize simplex with 10,000 dimensions, which is not really possible. Like, yeah, like you can do that again theoretically, but the exponential blow up of the number of states would be just too huge. Like that MDP would be really, really not possible to solve. Okay, so like this discretization doesn't really work. But for POMDPs and also for other things, right? Like we are learning and discussing this as a sort of canonical problem that you can also apply for other problems. And like for POMDPs, it's very interesting to like realize that, okay, like yes, the beliefs are continuous. We can have infinitely many beliefs because it's a probability distribution. But for each belief point, we are looking for some action. You know, so like technically, we want to find the best policy, and the best policy is like being able to play the best action in every possible belief point. And we have finite number of actions, right? Like this is like a key thing. Like we cannot really, or it's not really practical to discretize the belief space, but like we know that for each belief point, like we are looking for some best action. And that action can be actually very good for many belief points. Basically for some set of belief points. And this is what we will use. Right? So the fact that we have finitely many actions, it's like we can use it, so we will not like remember sort of mapping or hashing, like from this belief point play this action, from this belief point play this action. We will reverse it and we will say, okay, like we will have either some formula, and for every belief point we'll be able to compute what is the best action, or we can like map it and we will know that, okay, like this action is actually the best one for these belief points. So we can verify that. So how to do that? How can we like compute such a thing? So recall our example with the robot and belief point, this one, right? So we discussed, you know, it's a very simple belief, 50-50 between these two, and two actions, right? So how can we like formalize this, and how can we use this? Well, as I mentioned, the action or the reward for each action in each belief point is basically an expected reward. And we are computing the expected reward based on the probabilities with which we are in some particular state. So let's, for simplicity, assume that we have these two states, right? And so this would be our simplex. And let's say like this state, so we are in with probability, or the probability that we are in state 1 is 1 for this node, and probability that we are in S1 equals 0 for this node, where S1 is, for example, like that we are in that lower bottom corner of that maze. And we said that, okay, like if we are in that bottom lower corner, then like if we have action turn right, this is the best action for that state, so we'll have high reward. For this state, like the reward for that action is much lower, because like if we turn right in that right upper corner, like we are like facing away from the goal state, so our reward would be low. And like similarly, we can have like move backward reward for this state, and move backward for this state, right? And when we are changing the belief, the expected reward changes linearly as a linear combination of these points, because this is a line. So this corresponds to action A1, which is turn right, and this one is A2, move backwards. Okay, because like for every possible belief point, for every possible probability distribution, we can say, okay, so if I'm here, then like probability that I'm in this state is 0.8 or 0.9. So I will take 0.9 of this reward plus 0.1 of this reward, which is basically the linear combination of these two rewards. So for every action, I can like draw or create this linear function that computes these expected rewards. Right? And I can do that for basically any action and any belief point. And not only actions. I can do it also for every more complicated policy. Right? Because like this is only like one action, but I can also like have a similar policy, and I can compute it in a very similar way, because like when we have a longer plan for POM-DP, it basically consists of one action. Then the agent receives some observation, and based on that observation, we will reach a new belief point where again, like we want to follow up some action, and so on and so on, right? And this altogether is some contingency plan or a policy, right? So for every such a policy, I can have these linear functions, and these linear functions are called alpha vectors, and this is what we are going to use to represent the optimal and to find optimal policy, right? So why is that? Like let's imagine that like I can have like this these linear functions, and I can have it for like all actions, and one action is basically one step policy. Then, as I mentioned, like we can have two-step policies where I'm in some belief point, I can choose some action A1, A2, and so on. I can have multiple actions to choose from, and for choosing after choosing every action, I will receive some observation. I don't know which observation the agent is going to receive. I know the probability distribution with which I can receive a 1 or 2 and so on. I don't know which one I'm going to receive. But after each, receiving each observation, I will get to some belief point. B1, B2, B3, and so on and so on. And here, in these new belief points, I can continue in some other way. So for example, in here, I can choose action A4. In here, I can choose action A5. In here, I can choose action A7 and so on, right? And you know, like playing A1 is one-step policy in a POM-DP. If I want a two-step policy, I need A1 and then a mapping, like what will I do in this belief point, in this belief point, and in this belief point. So two-step policy can be A1, A4, A5, A7. Another policy, two-step policy, can be A1, A4, A5, A8. And that's different policy with different expected reward, because there is some non-zero probability that I will reach new belief point, and in that new belief point I will play different action with different expected reward. So the overall expected reward for this two-step policy will be different. So I can have some linear function that corresponds to my two-step policy P1. This is like one two-step policy that can be A1 and then like A4, A5, A7, and then I have P2 that can be almost the same, and here I will have A8, and like one of those linear functions can, for example, look like this. Another, you know, with that A8 can be, for example, slightly better in these parts of the belief space and can be slightly worse here. It will change a little bit. Not too much, because it really depends what is the probability with which I reach this belief point, but it can be different. And this is the point, that I can, for every policy, two-step policy, three-step policy, and so on, I can basically add these alpha vectors into this representation. And if I have infinite number of these alpha vectors, then basically I will approximate the true value function that we are looking for. Like if I have really all possible policies, then I have basically computed this. And then I'm done. Like if I have optimal value function, then I exactly know what I need to do, because for like every belief point I have a function that I will immediately find this is the best policy for this belief point, and I can just follow it. Right? So this is good. Like if I'm able to compute this, then I have solved the POM-DP. So this is like the idea, that we will use the finite set of actions, and from finite set of actions we can construct finite set of k-step policies. And as we expand this k, so how many steps we take in that policy, we are approximating some true value function v star. Like we are getting closer and closer to really the true optimal v star. We will never like completely reach the true v star, because like the policy can be infinite, right? But we can approximate it very, very closely. So this is, I would say, very, very important. So like if anything is unclear, just ask, because like this fact of that we can use these alpha vectors to approximate the value function and to get around this continuous variable. This is like the key observation, and we will like use it in the rest of the lecture. So, two main things. Like for each policy, which can be one-step policy, two-step policy, and so on, we can construct a linear function. And as we are adding more and more of these linear functions, we are approximating the V star or the value function that we are looking for POM-DPs. And each policy is a contingency policy, contingency plan, because we need to be able to specify what the agent is going to do, regardless of the observation that the agent is going to receive. Right? Like the agent knows that, okay, I can receive some of these observations, and these are the probabilities with which I will receive them. But in advance, I don't know whether I'm going to receive O1 or O2. I know that I will receive some of them. So if I want to have a proper two-step policy, I need to be ready and to have sort of prescription in that policy that, okay, for after this observation, I will play A4, because I'm in different belief state than when I receive observation O2. Okay, so these are like the important takeaways. Any questions? Okay, so when we have these alpha vectors, and I mentioned, like, we can build iteratively new and new alpha vectors. So basically, we can replicate the value iteration in a quite similar way to MDPs. So, like, whenever we are in some step T of the value iteration, we can basically use the value function approximation using alpha vectors, really as taking like the maximum of all these linear functions, because this is like the best the agent can do in each particular belief point. So for each belief point, like, we'll take the maximum, right? And so this way we can really like incorporate it into a value iteration style algorithm, where we'll just use this maximum representation as, like, this is our value function from iteration T, and then we will iterate through all the actions and all the observation that we can get, and we are looking for best new actions to be played in some particular belief point. So this is like how we can use it, but how do we construct the new alpha vectors from? And we have already touched on this when I discussed like these policies, right? Because since we have finite number of possibilities, we can just enumerate all the combinations, right? So we start with some action, and depending on observation, we can just change what are all the actions that will follow up after the observation, right? So this is true for going from one-step policy to two-step policies. But let's assume that I have some set of two-step policies, right? So I have these P1, P2, and so on, and these are all the two-step policies. So when I'm going to construct three-step policies, I will start again in some belief point, and I can choose some action, and then depending on the observation, I can choose from two-step policies. And this way I will have three-step policies. So I will create more and more of these alpha vectors, right? And again, like, this is thanks to the fact that this is finite and this is finite. So we have many, many possibilities, but we can enumerate them, right? So this is how we can construct new alpha vectors, and how we can basically iteratively add new and new linear functions that will more and more closely approximate the value function V star that we are looking for. Okay, so let's move to the example, which is like the best known example for POM-DPs. It's because it's very simple, and it's very difficult to visualize, these linear functions in more than dimension 2. So that's why, this tiger example is most often used to demonstrate the alpha vectors and how it all works. So let's have this very simple game where we have a contest where there is someone that wants to find the treasure behind one of the closed doors, and behind one door there is a treasure, and behind the second one there is a tiger. And of course, we want to find the treasure, and we don't want to find the tiger. So what are the possible states? We have only two states in this problem. The tiger can be either on the left side or on the right side. Whenever tiger is on the left, then the treasure is on the right, and vice versa. Right? So this is a simplification. We can have three possible actions in this problem. So we can either open the left door, we can either open the right door, or we can try to listen to improve or change, update our belief on the situation, and we try to learn where is the tiger. And when we are listening, we can receive one of two observations. Either we'll hear that the tiger is behind the left door, or we'll hear that the tiger is behind the right door. And what are the rewards? We get -1 reward for every listening action. So we need to pay for listening. We get +10 for opening the door with the treasure, and we get -100 for opening the door with the tiger. So this is the first part of the definition. What is the dynamic, and what is the initial belief, and how the belief can change? So we start with uniform belief point, because we really don't know where the tiger is. So it's 50-50. When we listen, we really don't change the state of the game. So if the tiger, or if we are actually in the state where the tiger is behind the left door, if we are listening, we are not moving the tiger around. So listening doesn't change the state of the game. If we open the door, the problem sort of restarts. So we go back to belief 50-50, and the dynamics can basically shuffle where the tiger is and where is the treasure. And if we are listening, then we can hear whether the tiger is on the left side or on the right side. However, there is a 15% error rate. So if we are listening and the tiger is actually behind the left door, we can hear with 15% probability that the tiger is behind the right door. Right? So far, previously, we had always, perfect transition with no errors. The actions always were completed with probability 1, and the observations were also with probability 1. In here, we have some error rate, right? And this error rate is 15%. So with 15%, we can get observation that is not really true what we would expect from the fact that we hear that the tiger is behind the right door. Sorry. Sorry about it. Okay. So this is the definition. So is it clear? Is the game clear? Okay. So how we can solve this? How can we do that? Of course, you would expect that, yeah, we want to open the door with a treasure. We don't want to open the door with a tiger. So most likely, we will start by listening, and trying to guess and estimate where the tiger is. So how can we do that? When basically we can write down and draw and prepare our alpha vectors, right? And this is what we can really do. And we can start with constructing our alpha vectors for one-step policies, which is basically like constructing the alpha vectors for every action, right? So we start with a belief point 50-50, where the expected value for listening is basically -1, right? Regardless of the belief point, the reward for listening is always -1. So it's a constant, right? So we can always listen, and we get -1. And if we open the right door, then our reward depends on where is the tiger. If the tiger is on the right, and we open right door, then we get the reward of -100. If the tiger is on the left, which basically means that the probability with which the tiger is on the right is 0, then we get reward of 10. Right? So this is the alpha vector for opening right door, and this would be the alpha vector for opening left door. Right, and this basically already approximates to, like, in this simple game, in this simple problem, it to some extent approximates like what is the best one-step policy for every belief point, right? And for this it can be quite enough, right? Because like we can say that, okay, like for all these belief points that are between, I think, 0.9 and 0.1, the best action is listen. And when like we move our belief to either this region or this region, in expectation, it's better to open that door. And of course, like we can be eaten in some cases for -100, but in expectation, it's already better, right? So like in this part of the belief space, open left is the best action. And for this belief space, open right is the best action. Right, so this is how we can approximate the value function v star. Questions? So this is, of course, like these are like one-step policies, and like let's say like we want to construct and find the best policy. So, for example, we need to know like how many times we should wait. So, depending on the observations, we need to update our beliefs, and we can use the Bayesian rule to compute like what would be the new belief if, let's say, we start in our initial belief 50-50, and we play action listen, and we have observation that we hear the tiger on the right side. So we can use our computation, and we know that we have started from initial belief. So the new belief for the fact that the tiger is on the right is that like originally like we had some probability 50%, and we received the observation here tiger right. So like there is a higher chance that the tiger is actually on the right. But we need to encounter, take into consideration that there can be an error in the observation, and with 15%, there is a chance that the tiger is actually on the left, right? So this way we can compute the new belief. So after listening once, if we hear that the tiger is on the right side, our belief now changed from 50-50 to 0.85, 0.15. And if we hear again, or sorry, if we listen again, and if we hear the tiger again on the right side, then like the belief will again move like closer to to here, that the tiger is on the right. Like so, like the more we listen, and receive the observation that the tiger is on the right, the higher the probability is that the tiger is actually on the right. It will never be 1, but we can approximate. And of course, whenever we like hear that the tiger is on the left side, with some 15% probability, our belief decreases. Right, so this is the dynamic, and for each of these policies, you know, like that we can construct, we can again similarly to before, we can construct a new alpha vector. So we can have this policy that will tell us, okay, like you need to listen 4 times if you have, for example, consistent observations, or some other number of times if you don't have consistent observations, and then based on all the observations you will decide either to open left door or the right door, right? So these are like this can be 2-step or multiple step policies, and we can put all in our representation of alpha vectors, and the more alpha vectors, the more policies we add, the more precise approximation we will get of the true value of this POM-DP. Okay. So, any questions to tiger example? For, you know, like as I mentioned, like the tiger example is used mainly because like it has 2 states and it can be easily visualized, like how the reward changes with states. But of course, like if we have, you know, 10,000 states, this simplex would just be with dimension 10,000, but the hyperplanes are still the same, and the idea is still the same, right? The only thing that changes really is the dimension, so it's difficult to visualize, but it's still like these are linear functions, so you can, you know, compute the value of these alpha vectors in the same way. It's just the dimension is changing. Yes? It basically depends on like whether there is some other external force, but in general, like this is the, I would say, similar problem to value iteration for MDPs as well. Like you don't really know when to stop. Like you can approximate, you can get closer and closer, but you don't have, you know, like that other information that, okay, now you are actually like sufficiently close, right? So this is, I would say, a very similar problem here. Like for in this simple example, it's kind of clear because like if you get closer in here and after playing that action, opening some door, the problem will restart without any like previous consequences. So really, like for this case, when you get here, it's better to open the door, right? But in general, you don't have to, like, you don't know that. So in general, you can basically add, and if the alpha vectors are not like changing too much, for example, for your initial belief, so you don't see, you know, like the changes that your policies are getting better and better, you can stop it. But you don't know, you don't have guarantees. Yes. Yes, Yes, basically, if you like, let's say you will keep adding, these alpha vectors with more listening into this, you will like find out that these new alpha vectors are actually like below those policies that, for example, listen only 2 times or 3 times. So your expected value will decrease exactly as you said. Like if you listen too many times, you just paid too much penalty. So like it doesn't pay off. So it's like in expectation, it will be better to listen only a few times and then take a shot. And like you will see that, right? Like I don't have, like the exact evaluation, but basically, like from initial point, like if you have an expected reward for a policy that should, let's say, listen 20 times, like for some cases, very very probable cases, then like that reward will be at least minus 20 or like minus, let's say minus 10 in the case that you actually find the treasure, right? So like you will definitely like not pick this as the optimal policy because it wouldn't be the highest reward, and the other policy that will listen only, let's say 4 times, will have higher reward. But thank you, very good question. Okay, any other question? Okay, so we have already, like hinted on this, that like we can basically enumerate all the possibilities and all the combinations, but of course, like when we are adding new and new k step policies and we are like increasing the k, then like every time, mainly because of this, like we don't know like which observation we are going to receive, and we can enumerate and create many possibilities depending on our continuation. Then the number of alpha vectors is like increasing exponentially with every step of the iteration. So this is not really like practical, right? Like depending on the number of observations, we can just like create exponentially many alpha vectors with each step of the algorithm, and this really will not scale well. So what we can do is that we can like prune out some of the alpha vectors that are dominated, and this is like what will happen in your case, where basically if we have an alpha vector that will like look like this, then basically it's not the best one in neither of the belief points. Like there is no belief point for which this alpha vector is the best one. So like we can remove these alpha vectors. We don't have to add them there. And if we, for example, listen too many times, like such alpha vectors would be dominated by some other alpha vectors, some other linear functions. So we can like slightly restrict these numbers of alpha vectors, but in general, like this will not like change the fact that we just need to go over exponentially many possibilities. So like we can prune it out, but it will not change the fact too much. So what is good to know and good to like understand is that when we are solving the POMDP in this way, like from the value iteration perspective, by adding really all alpha vectors, what we are doing is that we are really solving the whole POMDP for every possible belief point, right? Like we can solve really for all the points here, and we are trying to find the best action for everything. But when you were playing with POMDPs in a lab, and for example from the dynamic of the tiger example, you can see that like not really all belief points would be actually like reached through the dynamics of the game, right? Like some of the belief points are basically not reachable because the agent doesn't have actions or observations to actually get to that particular belief point. But in here we don't really know that, right? Like we are adding all the alpha vectors, all the possibilities for k-step policies, and we don't care whether particular belief point is actually important or not. So we can like use that, right? We can basically say that, okay, I'm not going to like remember all the alpha vectors. I can sample some important number of belief points, because these are important belief points for which I need to know like really the best action, but I don't care about the rest, right? And this leads to a family of algorithms that are based on so-called point-based updates and point-based value iteration algorithm. And the main difference is that like we will not add and remember all the alpha vectors. We'll just say, okay, I will have finite set of belief points, and I will remember only one alpha vector, one for each belief point. So every time, instead of having exponentially many and like exponentially increasing number of alpha vectors with each step of the iteration, we will just always remember only B number of alpha vectors, because we have one for every belief point. Right? So I will say, okay, I really need to know like what is the best action if I'm really close, for example, to the fact that tiger is on the left. I really need to know some belief points here. I want to like know what is the best policy for the initial belief, and so on and so on. So I can have some of these like crucial belief points, and like this way we can like significantly reduce the number of alpha vectors that we keep, and you know, like we get to something a lot more practical. You know, so this is a like visual comparison of all the alpha vectors that like you can get in the tiger example after some number of iterations, and like these are all the alpha vectors without point-based value updates. And if we say that, okay, like we want to keep only a fraction of this, we can get something that is basically very, very similar, right? So this is the main advantage. The main disadvantage is, of course, like it's easy to say that, okay, I'm just going to subsample the number of belief points and I will like keep information only about those belief points. The question is, okay, how you are going to subsample those important belief points? Because if we choose poorly, you know, like I have said that, okay, like I want to remember this one, and that one, because I had some background knowledge, like which belief points could be important for tiger example. But if we don't have that, it's not an easy way to say that which belief points are actually important, because we don't know which belief points are going to be important before we actually solve the problem. So what we can do is that, let's say that this diagram represents our simplex, and like these are all the belief points, right? So the whole triangle are all the belief points. So if we are optimizing in a value iteration style, we are optimizing everywhere. And the blue blob are only those belief points that are reachable when we are actually acting in the problem. So there can be situations where we cannot really like reach these belief points, right? Like these up here. Basically, like there is no combination of actions and observations that will get you there. So like you really don't need any alpha vector that would be best in this particular part of the belief space, because the agent will never get there. You don't need to optimize for that, right? So so there is some like blob of reachable belief points. So from there, like from this blob, from this set, you can start by sampling randomly, because at the beginning, usually like a random strategy is a good strategy. And then, you know, like as the algorithm progresses, you can refine the number of belief points that you want to keep, and you can sample more belief points in those areas where you like realize that it's more important to have more fine-grained information. And how can you like find this out? How can you know that? So for example, like if for a certain number of iterations, you will have the same alpha vector for 2 or 3 belief points, then you don't need those 3 belief points. Right? Like from the strategy perspective, it seems that for all these 3 belief points, this policy is already like the best one. It's not changing, it's not improving. So you can like discard the 2 and sample from other parts of the belief space. Right? So you can end up with fewer samples in certain regions of the belief space and more samples, for example, in those parts of the belief space where you need to distinguish like more precisely between different belief distributions. Right, so this is like the general idea, and like this is the basically first practical algorithm for solving POMDPs, and it removes the computational complexity for storing all the alpha vectors. It will not remove the computational complexity from the step, from the update. Like that is still like exponential, because like you will still need to choose from exponentially many alpha vectors in every step of the iteration, just because like there are really exponentially many combinations when you are considering extending your policies, right? So like, yeah, like the computation time-wise, it will be still exponential, but you will keep it, like you will manage to fit it into memory. So this is good. You know, like it will take a long time, but you have a chance to actually like get the result. So this is the advantage. You can solve, I would say, reasonably large POMDPs, which basically mean, let's say, small thousands of states, which already, you know, like it's much better than 2. So yeah, this is good. The main disadvantage, and this is the main disadvantage that I have hinted on the value iteration, is that like we don't know how far from the V star we are. And this is not just a problem of this algorithm. It's basically a problem in general. This is also true for reinforcement learning, right? Like you start your learning agent, and your agent learns. And you can see like how the reward, for example, improves over time, but you have no idea whether the true value of that problem, if you solve it perfectly, is like 100 or 1,000 or 1 million. You just see the delta, how your agent is improving, but you don't know like what is the true solution. You have no idea whether you are very, very close or whether it's like really garbage, right? Like you don't know. So this is also true for this algorithm. Like we just don't know. The second disadvantage is that like that set of belief points needs to be somehow maintained, like improved, and this like either requires domain knowledge or some other like heuristics and tricks how to work with that. So like yeah, this is a disadvantage. Okay. Any questions to point-based value iteration? If not, let's move to another algorithm that will actually help us with the issue of that is not clear, like how far we are from the optimum. And the like heuristic search value iteration is, let's say, an algorithm that I really like, mainly because it's very similar to what we did for like standard search in deterministic MDPs. Like we will have, and for example, other search that you can have in constraint optimization and so on. So it's a very like good demonstration of how the ideas from search can be applied in POMDPs and how it can help with solving POMDPs. So for HSVI, heuristic search value iteration algorithm, we will have 2 approximations of the value function. So we'll not only have this lower bound approximation that we had also so far, but we will have also upper bound approximation, right? So we will try to like have these two bounds, and we'll try to like get these bounds like closer and closer together as the algorithm will operate. And this way, like since we will have two bounds, we will know how far from the optimal we actually are. Because anytime, let's say this is our belief, like initial belief point. At any moment, we will have epsilon. That will be a distance between the lower bound and the upper bound in the initial belief point. And we know that the true value function, the true reward, if we solve this POMDP in an optimal way, is somewhere in this interval. So we know we have our bounds, like how far from the optimum we are. In the worst case, it would be the lower bound, but okay, it wouldn't be larger than epsilon. So we have some bounded error, which is good. You know, like now, like with HSVI, we'll know that okay, we need to continue further because we are too far away from the optimal solution. So, like, how would the algorithm work? The algorithm basically generalizes the point-based value iteration. So it will perform these point-based updates, let's say in a similar way that the value iteration did, but it will use the lower bound value function and the upper bound value function independently, right? So basically it's like two updates, one for the, like in a standard way as in point-based value iteration algorithm, and another update would be for the upper bound, for the optimistic estimation. So how would the algorithm work? We will start with some initialization, and then like we will select the belief points to be like for the update. And contrary to point-based value iteration algorithm, like we don't have a fixed set of these belief points where we are doing the update. These belief points where we are doing the update are selected based on like forward search through the problem. So we start with like the initial belief, and based on the upper bound, we select the best action and like move to another belief based on our observation. And again, like we select the best action based on the upper bound and perform the updates and move to another belief, and so on and so on. And at some point, like we will stop and then like propagate the changes upwards. So the belief points where the algorithm is making changes are not set, not fixed, but at the same time, like we don't perform updates for like all the belief space, right? So this is like the improvement from both point-based value iteration and the standard value iteration. So in this way, you know, like when we are doing the updates for both of these approximate functions, like you will see that we can get these functions together, closer together, and basically approximate the optimal solution. So what is like very interesting is to discuss, okay, so like we need somehow to start with these approximations. Like we need some approximations to start with, because you know, like we need to initialize these approximate upper bounds and lower bounds. And sorry. So the question is how to initialize. And again, like this is very common to other like problems that you want to solve. So you know, you have a POMDP, you have other type of problem, and you need to initialize the algorithm with some lower bound and some upper bound. So what would be a good representative of a lower bound? And try to think about search, try to think about like CSP or variant to the CSP with the optimization and so on. So what is a lower bound in any of these problems? In general. So it's a lower bound on not everything, so it doesn't have to be worst choice. It's a lower bound on the optimal solution. So basically, a lower bound on an optimal reward or on the expected reward of the optimal policy. Right, so from this perspective, like it doesn't have to be worst solution, it has to be a valid solution. Because that valid solution is lower bound because the optimal solution is only better, right? So like if we are looking for some policy, like the optimal policy is, you know, like the best one that gives us the highest expected reward. A policy, any policy, is a valid lower bound. So if we want to initialize these algorithms, we'll just take some policy. It can be random. It can be move always left. Any valid policy that satisfies maybe some other constraints that you may have is a valid lower bound solution, right? So, and this is also true for example, if you recall really the constraint satisfaction / constraint optimization, right? So any satisfying solution is a lower bound if we are optimizing also some other objective function. Okay, so this is the lower bound. How do we initialize the upper bound? And the upper bound is again upper bound on the expected reward of the optimal solution. Right, so this is something that we already have. This is something that you have already seen during this course. Because when it's upper bound on optimal solution, that's basically some optimistic heuristic. Right? Like I know that I will take my, for example, the cost to goal would be 10, and if my heuristic is optimistic, then it would be less in terms of cost and higher in terms of reward. So it's like higher value, it's upper bound, right? So how can we compute a good heuristic, optimistic value for a POMDP? Go ahead. Best action, well, like that would be the solution, right? But if you just want to quickly compute the heuristic value that would be like truly optimistic, and you want to have guarantees that like this is optimistic value. Okay, so yeah, you mean that we can take a constant of 10 here? Yes. Okay, that's a valid upper bound. Can we make it tighter? Can we make it not for this particular example, but in general? Like you're right. Like this is a valid upper bound, and we can use this, right? Like we can take the maximum reward that we can get, and we can make a constant, and that would be definitely upper bound. Sure. No argument there, but can we make it tighter with what you already know? Like, what was the rule of thumb when we want to create a heuristic function that is that we know that is truly optimistic? Sorry? Yes. And what that means, how do we like construct it? Like, what was the like typical rule that we use to create admissible heuristics. Yes, and like what was the general idea? Yes, but how do we design it? Like we had number of possibilities, like how to design it, and like there was one, you know, like a rule that okay, like we are solving more like complex problem, and we don't know how to solve it. So like how to deal with that to quickly compute optimistic heuristic or admissible heuristic. We can compute a simpler problem, solve a simpler problem. So for maze, we have removed the obstacles. There were no walls. This is a simple problem because it's then Manhattan distance, right? So we can, you know, solve a simplified problem. So in this case, what is the simplified problem? Sorry? Sorry, I don't hear you. Remove tiger, yeah, okay. Remove tiger is a simplified problem, but not for only tiger problem. Like when you what is the difficult part about POM-DPs? Difficult part about POM-DPs is that we don't know in which state we are. Yes, we see. Let's assume that we are not going to solve POM-DPs, but we are going to solve MDP, where we know exactly in which state we are. And this is a simple problem, because when we solve MDP, like it's definitely optimistic. Like we cannot be better and reach a higher reward if we don't know in which state we are, right? So if we add this information and we solve the MDP, this would be an optimistic heuristic. This would be upper bound to our value that we are looking for. Okay, so. Really, this is like the right way how to compute the upper bound for the HSVI. We just like create MDP from that POM-DP, assuming that we know the state we are, and this would be initialization. And usually it would be tighter initialization, that's just taking maximum reward everywhere. Okay, so this is how we initialize, and this is again, you know, like these kinds of connections are really important. Like this is why we are talking about this, because you see, like the idea that we are taking the simplified problem and solving that simplified problem is true for searching through the maze, but it's also true for POM-DPs, right? So this is what's important. How do we perform the updates? Basically, we have like two representations, like the updates for the lower bound is as before. We have alpha vectors that correspond to policies, and the upper bound is slightly different because we start basically with MDP like state values for every like point in the corner of the simplex. We have some point, and from these points we are basically creating lower convex envelope. So it's mathematically slightly more complicated, but basically again it's a convex function. And like during the updates, we are either like adding new alpha vectors, or we are like decreasing, adding new points into the upper bound representation, and you know like in this way we are really like tightening these two bounds together to get to this V star that we are looking for, right? So this is like how the algorithm like looks like when you visualize this. And this is again like the whole structure of the algorithm is again like very like common in AI, because similarly to search, similar to A star, like also in here, the algorithm is searching through the most promising actions, because the search is driven by the upper bound, right? So like the decision, like which actions to take and then to which belief points the algorithm like is going, is driven by the upper bound. So this is similar to like A star, where the search is or can be driven depending on the heuristic function, right? So this is very, very common, and like there is a clear idea why why the search is driven by the upper bound, because one of two things can happen. Either our upper bound was correct, and then like we will discover the good strategy, good policy, and we will have a good solution of the problem, right? So this is like one thing that can happen. Another is that our estimation in the upper bound was incorrect, it was too optimistic, and we will decrease it. Right? We will find out, okay, like this was too optimistic, this is not correct. We will decrease the upper bound for those particular belief points, and we will go search elsewhere. And in this way, like we are guaranteed that we will not miss optimal solution, because we know like what are the bounds and like whether there is some space to look for a better solution or not. And also we have always some basic solution that we are trying to improve over time. Right, so like try to like take this general idea and try to remember it whenever you will be constructing some search algorithm, because you know like the ideas from A star from here, like this can appear everywhere, and it can really be useful because it gives you guarantees. Like you know like whether to stop or not, and the optimistic heuristic can drive your search quite well. So this is to remember. And finally, like the best scaling algorithm, similarly to MDPs, like the best scaling algorithm is based on sampling and Monte Carlo tree search. So as with MDPs and games, we had MCTS as the algorithm that scales the best and can solve the largest problems. Here, for POMDPs, the situation is very, very similar. And we can solve POMDPs using Monte Carlo tree search like algorithm. And the algorithm is called POMCP. Like if you want to search for it, it's POMCP algorithm, and it's actually it was developed by co-founders of DeepMind when they were in academia. So they first started to work on POMDPs, and then they established DeepMind. So the main question, similarly to what we have already touched, is okay, like, but how to construct the Monte Carlo tree, right? Like we don't have states, or like we cannot really observe states. But again, like we can reuse the same idea that we used for constructing the policies for the value iteration, and we can construct the game tree with action observation histories. So we don't know like which states we are in, but we know what kind of actions and observations the agent performed, and this is something that we can use to build the tree and basically apply the same bandits and the same schema of Monte Carlo tree search to tree that is built using action observation histories. So we will not have like the state in the node of the tree, but we will have an action observation history in each node of the tree. And other than that, like you can just use the standard Monte Carlo tree search and UCT, for example, to solve POMDPs. All right, so this is not like the main trick. And the funny thing is that the Monte Carlo tree search and UCT algorithm was introduced for MDPs in 2006, and for POMDPs, the POMCP was introduced in 2010. So 4 years, all right. And if it's like that simple, just take action observation histories and you're done, then like it wouldn't take 4 years. Usually, like if it's that simple, then like people do it much faster. right? So where is the catch? Interestingly, even though that, for example, like we can exactly compute the exact beliefs because of like the Bayesian updates, so like we can enumerate exactly like what is the belief point, and therefore we can calculate exactly what is the expected value. You know from your own experience that for Monte Carlo research, like those rollouts and evaluations of the tree, they have to be very, very fast because you need to make a lot of them. And the larger the problem is, the more like iterations of these sampling methods you need. So even a simple thing like a belief update was delaying the algorithm too much. So like one of the key ingredients, and not the only one, was to use particle filtering. So basically just execute few random trials and then select based on those trials the next belief point, rather than computing it exactly, right? So like even though the idea is clear and you can like translate the idea from simpler domain to a more complicated domain, so from MDP to a POMDP, it still requires some additional technical work, right? And this is like one of the key takeaways. So what's important to remember from the POMDPs is how the policies look like, and that you need to know for two-step policy is to remember that I have some action, and then based on the observations, I need to have all these actions, all these continuations, because this is one policy. I need to know what I'm going to be playing in every belief point. So that's why like the number of possible policies grow exponentially. So this is one key takeaway. And then like one important observation was how to discretize the continuous space using finite set of actions and observations. And the fact that like the key ideas from simpler models to POMDPs, like it works. You know, like the ideas from A*, from Monte Carlo sampling, it's possible to adapt them. And it will be possible for you to adapt them on the problems that you will be solving later in your life. But like the more complicated the problems, then the, you know, it's always said that the devil is in the details. So those technical details can be actually challenging to overcome and to resolve. But the idea is still there, and that idea can work. So this is the important part. So that's it. Thank you very much, and see you next week. Not next week, but the week after that.